Hi guys, let's take a couple of days and let's talk about continuity. Continuity is a huge topic. We'll try to break things up to where we toggle between the lesson and the homework, and you're able to work together off and on through the rest of today's class and then all of tomorrow's class. And then plan on coming in Thursday morning and asking me just as many questions as you need to, okay? So, with continuity, it's important that you know the three-part definition and that you know how to apply this definition whenever you need to write whether a function is continuous or not at a specific x value. So if a function is continuous at a specific x value, and we'll say x equals c, then three conditions must be met. Conditions 1 and 2 could technically be inverted. So you could first determine whether the limit exists at x equals c. And then second, you could determine whether the function exists at x equals c. It would also be okay to reverse the order of those two and find out whether the function exists first and then whether the limit exists second. Now, the third for sure condition you must meet is to say that the two things you've already looked at, the limit value and the function value, you've got to say that they are equal or they are not equal. Well, you are used to us talking about things both informally and formally. So when we talk in class, we're often going to be informal, but we're going to be using good calculus concepts. But whenever you're asked to write about continuity, you've got to learn the formal lingo, and that can be challenging. Well, okay, so let's start with informal. There are three types of discontinuities, or three reasons a function can fail to exist at a specific x value. Number one, holes. Two, poles. Three, jumps. So saying holes, poles, and jumps has just a nice ring to it. It's easy to remember. You know what holes in the graph are. So you can see for both of my examples at f of x, I've got a hole in the graph. In the first example, the line has a hole in the graph that's not been filled elsewhere. And then in the second f of x example, the parabola has a hole in the graph that has been filled elsewhere. Regardless of whether you fill the point elsewhere or not, that's a hole in the graph. It's pretty easy. Now, sometimes we call holes in the graph removable discontinuities, particularly in the case of the first f of x. So for functions like this, I'm going to try to write with a pen. That's oftentimes more profitable here. But for functions like this, we'll often talk about filling the removable discontinuity. And you do that by creating a piecewise function. So we'll get to that later in this lesson. Poles is just a snazzy way of saying vertical asymptotes. And then the third kind of discontinuity is a jump discontinuity. So your typical jump discontinuities are with the h of x that is the absolute value of x over x. You know that that's a single equation that creates the jump discontinuity. Most of the time, however, jump discontinuities are created when I make up some piecewise function for you. So those are the different kinds of discontinuities. All right, so I told you a minute ago we would talk about a function with a removable discontinuity. Remember, a removable discontinuity is just a fancy way of saying a hole in the graph. So let's start out by graphing. Well, what kind of function is f of x? Well, it's got a fraction in it. Oh, that means it's rational, fractional. And you know that the first thing that we always do when we're graphing rational functions is to factor. And if any factors cancel out, you cancel. So I quickly see that f of x is going to be x plus 1. And there's going to be a hole in the function at x equals positive 1 since the factor x minus 1 canceled out. Okay, so that's pretty darned easy to graph, isn't it? So let's see here. I'm going to graph my function. And if it's x plus 1, I obviously know the y-intercept is 0, 1. And I'm going to travel up 1 I love this board. I'm going to travel up 1 over 1 and up 1 over 1. And I'm going to draw my line. Now that I've got the line drawn, I need to go back and erase the hole at 1. Okay. Again, I'm trying to erase the hole out, but y'all can see that. Okay, I'll do it that way. Y'all can see that I'm having some trouble with the board, trying to make it touch where I want it to. All right, I'm about to give up, guys. And I'm sorry because I don't want to waste your time watching the video while I'm trying to make the board right where I want it to write. All right, so I have shown the graph with a hole in the graph. All right, and it says specifically name the hole in the graph. Well, I mean, I could do that pretty easily. I can see that the hole in the graph that I erased out is specifically at the point 1, 2. All right, that leads us to the ability to rewrite the equation of f of x as a piecewise function that removes the discontinuity. FYI, when it says remove the discontinuity, it's saying fill the hole. Okay, what's that mean? It means at a point to the graph that fills that hole. So once you realize that, it's not as hard as it kind of looks like it is by the definition. So I'm going to say, okay, well, let's call g of x my new function, and it is going to be the exact same as f of x with the hole filled. So all I have to do is say, okay, well, take the equation that you had for f of x, and that's a great equation everywhere except at x equals 1. So say everywhere except at x equals 1. X does not equal 1. Then what you want to do is I want to come through and fill the yellow hole. Wow, I was able to fill that in one try. That's pretty good. So that means I want my y-coordinate to be 2 when x equals 1. So I'm adding the point 1, 2 back into the graph. That is all it means to have a removable discontinuity and to rewrite the equation that fills or removes the discontinuity. All right, so we've talked about this whole informal, formal thing. Well, I tell you what, why don't we go through and talk informal first? So do you see at x equals -4? So x equals -4 is right here on the number line. All right, what kind of jump or what kind of discontinuity do we have right there? Well, I just answered by accident. It's a jump. So we'll say there is a jump discontinuity. And I'm just going to leave it at that for my informal statement. All right, well, what about at -1? Well, of course, here's x equals -1, and I see that the issue is that the graph is not continuous as a trace because there's a hole in the graph. And then at x equals +1, okay, now wait a minute, everything's good. Here's x equals +1. Everything's fine. There's not a hole in the graph there. There's not a pole, i.e. a vertical asymptote, and there's not a jump. So at x equals 1, the graph is continuous. All right, what about at x equals 3? Well, of course, at x equals 3, I see a vertical asymptote. And then last but not least, at 5, 1, 2, 3, 4, 5, here's x equals 5. Again, it's like at x equals 1, the graph is just nice and continuous. So we're going to practice explaining why a graph is continuous and discontinuous so that you understand how to write your formal reasons. Okay, so let's look at the discontinuities, we'll look at the discontinuities first. Now remember, you've got to do a 3-part test. The first 2 parts or to do f of and talk about the function value, and the limit as x goes to and talk about the limit value. If you pass the gate on both of those, then the third thing you look at is whether those two values are the same. Well, take a look at x equals -4. All right, well, the issue here is not that f of -4 does not exist, but do you see that the limit does not exist at x equals -4? So I would say something like the limit at x goes to -4 from the left of f of x does not equal the limit as x goes to -4 from the right of f of x. Well, what's that tell us? So I know that means that the limit as x goes to -4 of f of x does not exist. Okay? So that would be the reason that I have a jump discontinuity. So again, this is me saying that f of x is discontinuous. I'm going to abbreviate at x equals 4, -4, excuse me. And it's because the left-hand limit does not match the right-hand limit, which causes the overall limit to not exist. So this does not meet one of the first two required criteria. All right, we'll take a look at x equals -1. So I've already said that f of x is discontinuous at x equals -1, and my informal reason is that there's a hole in the graph. But again, take a look. Is the issue that f of -1 does not exist? Well, no, because I see there's a point -1, 1, so f of -1 does exist. Is the issue that the limit as x goes to -1 does not exist? Well, no, because I see that if you trace the left-hand part of the graph and the right-hand part of the graph, as you go toward x equals -1, the left-hand limit and the right-hand limit are both converging to the hole in the graph at -1, 3. So what's the issue? The issue is that the limit value does not equal the function value. So I'm going to say the limit as x goes to -1 of f of x equals 3. But that does not equal 1, which is f of -1. So here I'm kind of doing two things in one statement, and you can do this as a 1 and then a 2 and then a 3 if you like that better. But if I go ahead and find the limit value and find the function value, and the issue is not that I don't satisfy one of the first two criteria, the issue is that I don't satisfy the third criteria, I'm going to go ahead and say, well, let me find these two values and show you that they are not equal. And then I'm done. I can write it all in one line. All right, so let's look at x equals 3. So again, I'm going to say that f of x is discontinuous at x equals 3 because, okay, so let's go back to the graph at x equals 3. That's where my vertical asymptote is. Okay, do you notice that at x equals 3, the limit does not exist because there's unbounded behavior? Do you also notice that f of 3 does not exist? So all I have to do is pick one of the two reasons, and either one of them is enough to kill the continuity. So I might say f of 3 does not exist because that's actually a little bit shorter to write. But you could also say the limit as x goes to 3 of f of x does not exist. So say one or the other. It would be all right to say both as well. Um, but what you can't do, and what people want to do, because people start getting crafty and thinking that they'll just say f of 3, I'm going to erase this, so don't worry about writing this down, but f of 3 does not equal the limit as x goes to 3 of f of x. So people start thinking I'm just going to write that everywhere and cover my bases. You can't write that, because if you say that the left side doesn't equal the right side, you're implying that the left side does exist and is some finite value, and that the right side does exist and is some finite value, and the two finite values are not a match. So you can't get to step 3 until you've bypassed the conditions for both step 1 and step 2. And I know it would be awesome if that would work, but it doesn't. But I have had crafty calculus students try to do that in the past. It's just, it won't work. It doesn't hold water. All right, so let's look at 1 and 5. Once you know how to do 1 or 5, it's the same thing. So I'm going to do 5 right now just because I have a little bit more room to write. And then I'm going to say the same exact thing for x equals 1. So what I'm asserting here is that f of x is continuous, and again I'm going to abbreviate, and I'm going to fix the mess that the board's making for me. Is continuous at x equals 5 because, all right, well, if I do the function value first, what is f of 5? Well, I'm seeing the point right here, 5, negative 1. So I'm going to say f of 5 is equal to negative 1. All right? And that also equals the limit as x goes to 5 of f of x. Because again, if I trace toward x equals 5 from the left, and I trace toward x equals 5 from the right, I'm also from the left and right meeting at that point 5, negative 1. So that does it. So I could say right quick the same thing about 1 now that I know the structure. F of x is continuous at x equals 1 because f of 1 is, now when I look at f of 1 it looks like it's 0, and that's equal to the limit as x goes to 1 of f of x. So it always has to come back to your formal definitions. So if you want to say that a graph fails to be continuous, you have to use the formal notation to prove a hole, a pole, or a jump. Just like if you want to prove that a limit fails to exist, you have to go back to the notation to say that the left-hand limit does not match the right-hand limit, or that there's unbounded behavior from the left or from the right, or oscillation, but that's not really one you're going to get into. So now let's look at a function and whether it is continuous on a closed interval. All right, so the first thing we're going to do when you have one of these is just to graph it. So do you recognize that k of x is an absolute value v-shaped graph that's upside down and it's moved left 3 down 2. So I'm going to say left 3 down 2. All right. And I'm supposed to draw the graph from negative 5 to 0. So let's see here. If I plug in negative 5 plus 3 is negative 2. The absolute value of negative 2 is 2. Times the leading negative is back to negative 2, and then minus the 2 on the end is negative 4. And I believe if I think about it, because I can tell the slope is out 1, down 1, so out 1, down, out 1, down 1, and then out 1, down 1. So I'm just going to draw the graph on the closed interval. So that worked out okay. Sort of. And then I'm also going to go out 1, down 1 to the right. So if I do that and I use symmetry, let's see here. I know that this point will be a point in the graph. Let me draw one more point in, And then I should have 0, negative 1, 2, 3, 4, 5. Is that right? Let me double check that. So 0 plus 3 is 3. Absolute value is still 3. Times a negative is negative 3. Subtract the 2 on the end is negative 5. So yeah, we've got it. Now, I mean, I can see that the graph is continuous because between x equals negative 5 and x equals 0, there are no holes, there are no poles, there are no jumps. So everything's good. What you basically look for is to say, yes, on the open interval from negative 5 to 0, I see that there are no holes, no poles, no jumps. Now, if you want to additionally show that the graph is continuous on a closed interval, what you've got to do is look for one-sided continuity. So I would have to say, well, is x equals 5, or is k of x continuous at x equal negative 5? Because, so we're going to go back to the three-part test. Okay, what is k of negative 5? Well, I think we said that k of negative 5 is equal to negative 4. Furthermore, the limit as x goes to negative 5 of k of x is equal to negative 4. But stop. K of x doesn't go to negative 5 from both the left side and the right side. The graph only goes to negative 5 here from the right side. So add a plus there. Add a plus there. So now you've proved that k of x is continuous from the left and of negative 5. So that sort of gives you a reason to say, yes, I can bracket negative 5. All right. So now let's show that k of x is continuous on the right-hand endpoint. So k of x is continuous at x equals the right-hand endpoint, which is 0, because k of 0 equals negative 5, and that's also equal to the limit as x goes to 0 of k of x. So right now I'm writing just sort of that cookbook sort of definition, but now let me be more specific, okay? You know that what you've got to do is look at the limit as I go to x equals 0, but that only comes from the left, so I've got to add the little left symbol there. And again, saying that is what allows me to say that the graph is not just continuous on the open interval with parentheses, but also on the closed interval. So we keep coming back to that definition. All right, so discuss the continuity of g of x, is the greatest integer function at x equals 2. Okay, so let's start with graphing it. All right, so I'm only going to graph the part of the graph that I need to look at. So I'm not going to worry about graphing a lot of stuff in the third quadrant. So I've got 1, 2, 3, 1, 2, 3. And I know, for instance, I'm going to do this in black just to make it stand out. I know that g of 0 is 0, g of 1 is 1, g of 2 is 2, and g of 3 is 3. And then I know that when I plug in 0.1, 0.2, 0.3, 0.4, yada, 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 all the way up to 1, that I always rebound back to 0. Oh, yeah, well, here I go again. I am sorry, guys, that this is wasting some of your precious time here to watch me mess with the board. But now I remember that what I've got to draw is the little horizontal steps that are open on the right and closed on the left. So I've got enough. I think the hole in the graph at x equals 1, 0 is big enough, don't you? So I've got it graphed. Now let's look at the limit as x goes to 2 from the left. See if we can pull that one off. So the limit as x goes to 2 from the left of g of x equals, well, let me use some color. Here's x equals 2, obviously. And if I look at what's going on as I'm coming to 2 from the left, My left hand coming from the left, I'm going to the hole in the graph at 2 comma 1. So that left hand limit's 1. All right. Well, let's look at the limit as x goes to 2 from the right of g of x. So let's see what's happening there. So when I head toward x equals 2 from the right, that means I would be tracing this higher step. And when I trace the higher step, I'm going toward the point at 2, 2. So the right-hand limit's 2. All right, so is the graph continuous at x equals 2? Well, no, because the limit does not exist at x equals 2. So g of x is discontinuous at x equals 2 because the limit as x goes to 2 of g of x does not exist. And I know that because I looked at the left-hand limit and the right-hand limit and they didn't match. All right, so give a formal statement supporting continuity or discontinuity, which we've completed. So we've gone through steps 1, 2, and 3. Now, question. Could you say that the g of x is continuous from the left or right at x equals 2? Well, I hope you see that you could say that the graph is continuous from the right-hand side, which was the step I've outlined in green. From the left-hand side, it's not because there's a hole in the graph. But I could say the green step shows that g of x is continuous at x equals 2 from the right. Now, why would that be? So we're going to go straight back to our definition. What is g of 2? Well, again, g of 2 I see right here on this left end of that step. G of 2 is 2. And that's equal to the limit as x goes to 2 from the right-hand side of g of x. So we can sometimes talk about one-sided continuity, and we did that a minute ago with the closed interval, and now you see another place where we're doing a similar sort of thing. So let's stop there and pick up in just a little bit.